Question 12a. Two beakers, one containing water and another containing glycerin, are drilled with sticks at equal angular speed and left at a time then which liquid comes to rest first and why. So let us understand the meaning of drilled. Okay, so it mean to turn around circle or circles. Okay, so we have this. Now in this question 12a, okay, we have two beakers. We have two beakers. Clear? We have two beakers. One containing water and another containing glycerin. Okay, and the liquids are made to turn around circles with the help of sticks. So we have this sticks, and the angular velocity of the liquids are omega. Okay, so I'm writing over here. They are rotated with same angular velocity or speed omega and are left for some time to come to rest. So we have this. Then we need to explain which liquid comes to rest first and why. So we have this. So in order to understand this question, we must compare viscosity of glycerin with viscosity of water. So I'm writing viscosity of glycerin. Okay, this equals 0.83 Pascal second at 20 degrees Celsius and 0.63 Pascal second at 30 degrees Celsius. So we have this. Clear? We have this. And next, viscosity of water. Okay, so the viscosity of water is 1.8 times 10 power minus 3 Pascal second at 0 degrees Celsius and at 20 degrees Celsius. Okay, the viscosity of water is 1. So I'm writing in this way. Okay, so we have this, and at 30 degrees Celsius the viscosity of water is 0.80 times 10 power minus 3 Pascal second. So we have this. Clear? Now, when we compare viscosity of glycerin with viscosity of water, we find glycerin is more viscous than water. So I'm writing, we find glycerin is more viscous than water. So due to this, okay, due to this, what we find, due to this, the relative motion between different layers of glycerin, okay, is more strongly opposed compared to water. So we find different layers of glycerin, okay, are more strongly opposed in comparison to water. So the layers of glycerin are more strongly opposed in comparison to water. So we can tell, okay, so glycerin will come to rest earlier than water. So we have this. Now next, okay, question 12b. Question 12b. Water flows through a pipe. Let us consider a horizontal pipe, okay. So we have a horizontal pipe and let this be the axis of the pipe, okay. So I'm drawing in this way. This be the axis of the pipe. So this is the axis. So we have this. Now what we find, which of the layers moves faster? So we find different layers, okay, of liquids moving with different, okay, velocity. So we have this. Clear? We find this. Now what we find, the layer, okay, the layer in contact, okay, in contact. So we have this, the layer or the layers in contact with the pipe, okay, with the surface of the pipe, moves with zero velocity. Moves with zero velocity. And as we move from surface to the axis, okay, in this direction, and as we move from surface to axis in this direction, then we find the velocity of the layer goes on increasing and is maximum for the layer moving along the axis. So we have this, okay. So for this layer, okay, the velocity is maximum. So for this layer, okay, velocity is maximum. So I'm writing, okay, when a viscous, okay, when a viscous liquid flows horizontally through the pipe, okay, the layer of liquid in contact with the wall or surface, okay, of the pipe has zero velocity, okay, has zero velocity, that is remains stationary. Clear? And the velocity is maximum along the axis of the pipe. Therefore, the layer moving along the axis of the pipe moves faster. Now, question 12C, okay? 2 drops of liquid of radii Rn R/2 with terminal velocities V1 and V2 respectively. Find the ratio of V1 to V2. So, 12C, we have 2 drops, okay? One having radius R, and next, okay, small drop having radius R/2. Clear? So we have this, and this is moving with terminal velocity V1, and this is moving with terminal velocity V2, and we are asked to find, okay, this is V2, we are asked to find the ratio V1 by V2. So we are asked to find this. Okay? We are asked to find V1 by V2. Okay. Now we know the general expression for terminal velocity. Okay. We know terminal velocity Vt equals 2 by 9 r square rho minus sigma g divided by eta. So we have this. Clear? We have this. Now in this expression, okay, we have r, the radius, okay. So this is general expression. This is the radius of body, okay, moving in the fluid, okay. And rho, this is density of body. So we have this. And sigma, this is density of fluid. So we have this. And eta, this is coefficient, okay. This is coefficient of viscosity of fluid. Now we have in this question, okay, 2 drops of liquid having radius Rn R/2. So we have radius. So in this question, okay, we have radius. So let me write in this way. We have radius given, okay, for 2 drops, and we have terminal velocity given. So we can write in this way, okay, terminal velocity Vt is proportional to square of the radius. So we have this. Clear? Therefore we can write in this way V1 by V2, okay. We know terminal velocity is directly proportional to square of the radius. So we can write in this way. So this equals R by R/2, and whole power is 2. So we have this 2R by R whole power 2. So we can cancel this. So we get 4, okay. So we can write in this way 4 by 1. Therefore, ratio of terminal velocity V1 to V2 equals 4 by 1. So we have this. Clear?